Picture humanity as contestants on the universe's strangest game show, and 3i Atlas just revealed our prize options. Behind door number 1, revolutionary science that transforms our understanding of planetary formation. Behind door number 2, a quiet past that changes nothing except textbook footnotes. Behind door number 3, well, that's where things get interesting. Like cosmic Russian roulette played with interstellar objects, every new visitor presents a ranked menu of possibilities, some delicious, some dangerous, most surprisingly mundane. But in the case of 3i Atlas, mundane is the last thing that comes to mind. We've catalogued every potential outcome from transformative discovery to tabloid nightmare. Stay with us to learn which prize humanity is most likely to win and which scenarios await us in the coming months. Part 1. What 3i Atlas is and why it matters. In the summer of 2025, something changed forever. Not with fanfare or warning, but with the quiet click of a camera shutter in the Chilean mountains. What Atlas saw that July 1st night was nothing short of extraordinary, a visitor that had travelled for millions, perhaps billions of years, just to pass through our neighbourhood. Meet 3i Atlas, the third confirmed interstellar object ever discovered. While you were sleeping, while you were working, while humanity carried on with its daily routines, this ancient wanderer was already racing toward our sun at 57 kilometers per second. That's fast enough to circle Earth in 12 minutes. Fast enough to leave our solar system behind forever, but speed alone doesn't make something interstellar. What marks 3i Atlas as truly alien to our system is its orbit, a hyperbolic trajectory with an eccentricity of approximately 6. In the language of celestial mechanics, this means one thing: it will never return. Unlike the comets we're familiar with, which swing around the sun in predictable ellipses like cosmic boomerangs, 3i Atlas follows a path that bends but never closes. It came from somewhere else entirely, and it's going somewhere else entirely. The discovery unfolded with the methodical precision that defines modern astronomy. First detection, July 1st, 2025, captured by the Asteroid Terrestrial Impact Last Alert System telescope in Chile. But astronomers are careful people. They dug deeper, scrolling through archived images, searching for earlier glimpses. They found them. Pre-discovery observations stretching back to June 14, 2025, revealed that this visitor had been silently announcing its presence for weeks before anyone noticed. The official designation followed quickly: 3i, meaning the third interstellar object; Atlas, honoring the survey that found it. Behind this bureaucratic naming lies something profound. We now live in an era where visitors from other star systems are common enough to require a filing system. Where is it going? The mathematics are unforgiving and precise. Perihelion, the closest approach to our Sun, will occur around October 29th to 30th, 2025, at approximately 1.36 to 1.4 astronomical units. That's roughly 204 million kilometers from the Sun, placing it somewhere between Earth and Mars at its nearest point. For those keeping track of existential threats, 3i Atlas will pass closest to Earth in mid-December 2025 at about 1.6 to 1.8 astronomical units, roughly 270 million kilometers away. To put that distance in perspective, it's further than the gap between Earth and Mars at their closest approach. There is zero impact risk, none. The mathematics of orbital mechanics don't deal in maybes when it comes to trajectories this well defined. But what exactly are we looking at? Early observations with the Hubble Space Telescope on July 21st revealed something both familiar and alien: a teardrop-shaped dust coma, the hallmark signature of a comet awakening under the Sun's influence. Size constraints from these first glimpses suggest a nucleus no larger than 5.6 kilometers across, though it could be significantly smaller. We're not talking about a mountain-sized chunk of ice and rock, more like a large hill with delusions of grandeur. Yet size, as we'll discover, may be irrelevant compared to what this object carries within its ancient structure. Here's what we know with confidence. 3I Atlas is definitely interstellar, definitely active, and definitely safe. Its orbit class is confirmed, its rough activity level is measurable, and its distance from Earth is comfortably vast. But here's what we don't know: the exact size of its nucleus, its precise shape, its detailed composition, or most intriguingly, the specific stellar nursery where it was born. This uncertainty isn't a failure of science, it's the edge of discovery, the place where known facts meet infinite possibility. Why does any of this matter? Because 3I Atlas carries within its frozen structure a chemical fingerprint from another solar system. While Earth's comets formed in our Sun's disk 4.6 billion years ago, this visitor formed around a completely different star, under different conditions, with different materials available. It's a geological sample from a world we'll never visit, delivered directly to our instruments. Every molecule of water ice, every grain of dust, every trace of carbon monoxide represents a data point in the grand experiment of planetary formation. How do other star systems build their worlds? What materials were common in the ancient galaxy? How similar or different are the processes that created Earth's neighborhood? 3I Atlas offers answers, but only if we're smart enough to ask the right questions and sophisticated enough to interpret what we find. The name itself tells a story. Atlas, the Asteroid Terrestrial Impact Last Alert System, was designed to spot potentially hazardous objects, the kind that might one day threaten Earth. Instead, it found something that poses no threat, but offers something far more valuable: perspective. We are not alone in this galaxy, not in the sense of little green men, but in the sense that planetary systems form, evolve, and occasionally share their leftovers across interstellar space. As we embark on this investigation, we'll separate what we know from what we hope, what's been peer-reviewed from what's still being debated, and what's scientifically sound from what's pure speculation. The truth about 3I Atlas is remarkable enough without embellishment. We stand at the threshold of discovery, watching an ancient traveler make its brief appearance in our cosmic backyard. What it teaches us may reshape our understanding not just of comets, but of how planetary systems across the galaxy build themselves from dust and dreams. The question isn't whether 3I Atlas will change everything, it's how much, and in what ways, we're prepared to let it. Part 2. Tier Outcome: The Scientific Windfall. What if everything we thought we knew about comets was wrong? What if the neat categories we've built, water-rich, carbon monoxide enhanced, typical this, normal that, were just the limited perspective of creatures who'd only ever seen comets from one star system? 3I Atlas is rewriting the textbooks in real time. The first bombshell came from the James Webb Space Telescope, humanity's most sophisticated eye in space. JWST's near-infrared spectrograph detected something that made astronomers double-check their instruments: unusually strong carbon dioxide emissions compared to water. Early estimates suggest a ratio approaching 8:1, 8 parts carbon dioxide to every 1 part water vapor. For context, typical solar system comets show the opposite pattern, with water dominating the chemical mixture. This isn't just unusual, this is extraordinary. But JWST wasn't alone in its surprise. The FEREX mission, designed to map the entire sky in infrared light, turned its attention to 3I Atlas and discovered something even more puzzling. The carbon dioxide coma, the cloud of gas and dust surrounding the nucleus, extends for at least 348,000 kilometers. That's nearly the distance from Earth to the Moon. Meanwhile, water and carbon monoxide, the substances that typically announce a comet's presence, were not detected in those observations. Now, before we get carried away, let's acknowledge what we're dealing with. These are preliminary results, the kind that makes scientists both excited and nervous. The teams analyzing this data are still refining their measurements, still double-checking their calibrations. What we're witnessing is science in action, the messy, iterative process of turning raw data into understanding. But even with appropriate caution, the implications are staggering. The carbon dioxide dominance suggests two primary scenarios, each with profound consequences for our understanding of planetary formation. First possibility: 3I Atlas formed beyond the carbon dioxide ice line in its home star system, in the frigid outer reaches where carbon dioxide freezes before water does. This would place its birth in the equivalent of our outer asteroid belt or beyond, in the cold, dark regions where only the most volatile substances remain gaseous. Second possibility: the nucleus has developed a surface crust that effectively suppresses water sublimation while allowing carbon dioxide to escape. Think of it as a cosmic thermos bottle, with an outer layer that insulates the interior and controls which materials can outgas under solar heating. Both scenarios require us to fundamentally reconsider models of how outer protoplanetary disks distribute their chemical ingredients. We're not just looking at one weird comet, we're potentially glimpsing an entirely different approach to building worlds. The coordination of observations across multiple facilities represents a masterclass in modern astronomy. JWST provides the detailed molecular fingerprints through its near-infrared spectrograph. Hubble captures the morphology and size constraints with its incredible resolution. SPHERICS maps the extended environment with wide-field spectral coverage. Ground-based telescopes at Gemini Observatory and NOILAB add complementary imaging and spectroscopy from Earth's surface. Each instrument sees something different, but together they're assembling a portrait of an object unlike anything in our solar system's family album. The comparative context makes 3I Atlas even more intriguing. 2I/Borisov, our previous interstellar comet visitor, behaved like a perfectly normal comet, water-dominated, predictable, familiar. It fit comfortably into our existing understanding of how comets work. 1I/Oumuamua, our first confirmed interstellar visitor, was so unusual that astronomers are still debating whether it was a comet at all. Some evidence suggested it might have been more asteroid than comet, or something else entirely. 3I Atlas fills a crucial gap in this small but growing catalogue. It's definitely a comet, the dust coma and outgassing leave no doubt. But it's a comet that challenges our assumptions about what normal means in the broader galaxy. The payoff extends far beyond comet science. Volatile ratios like the ones 3I Atlas is revealing help astronomers locate birth zones and reconstruct thermal histories in protoplanetary disks across the galaxy. Every star system builds itself differently, using whatever raw materials are available and following the specific dynamics of mass, temperature, and time. By studying the chemical signatures of interstellar visitors, we're essentially conducting archaeology on planetary formation processes that occurred billions of years ago around stars we'll never visit. The data legacy aspect deserves special attention. Unlike fleeting phenomena that disappear forever, astronomical datasets tend to improve with age. The raw images and spectra being collected now will be reanalyzed for decades to come as calibration techniques improve and new analysis methods are developed. NASA and ESA maintain open archives specifically for this purpose, ensuring that today's observations become tomorrow's breakthrough discoveries. This global campaign represents coordination at its finest. Observing windows have been carefully orchestrated to maximize science return, even though Earth will be poorly positioned during perihelion when 3I Atlas swings closest to the Sunday. Spacecraft scattered throughout the solar system will pick up the observations when ground-based telescopes lose their view, creating a continuous record of the comet's evolution. The theoretical implications ripple outward like waves from a dropped stone. If 3I Atlas truly originated in the galactic thick disk, a population of older, metal-poor stars formed during the galaxy's youth, then we're examining material that predates Earth's formation by billions of years. We're literally holding a piece of cosmic history in our scientific instruments, a sample from an era when the universe was fundamentally different. But let's be honest about the controversy. Active debate continues about whether 3I Atlas comes from the thick disk or the thin disk, whether its parent system was ancient or relatively recent, whether its unusual chemistry represents primordial conditions or later evolution. Science thrives on such disagreements, using them as fuel for better observations and more sophisticated analysis. The jackpot here isn't spectacle, it's precision. While the general public might hope for dramatic photos or visible tail displays, the real treasure lies in sharp chemical signatures and precise dynamical measurements that constrain models of how planetary systems form across the galaxy. Every spectral line, every velocity measurement, every photometric data point represents a piece of evidence in the grand jury trial of planetary formation theory. 3I Atlas is teaching us that our solar system, for all its familiarity, represents just one approach to building worlds from cosmic dust. Other stars, other systems, other approaches exist. And occasionally, if we're very lucky and very prepared, those other approaches come to visit. The question is no longer whether interstellar objects will revolutionize our understanding of planetary formation. The question is how quickly we can learn to read the messages they carry. Part 3. A. Tier Outcome, Mission Alignment, and Tech Spillovers. Sometimes the most profound discoveries happen not because we build something new, but because we're clever enough to point existing tools in the right direction at precisely the right moment. The beauty of 3I Atlas lies not in requiring some massive new space mission, though that would be exciting, but in how it perfectly aligns with humanity's existing scientific infrastructure. We don't need to spend billions of dollars or wait decades for launch windows. We just need to be smart about coordination and opportunistic about timing. The reality of modern astronomy is that the most capable instruments are already in space, already operational, already delivering groundbreaking science on a regular schedule. JWST is revolutionizing infrared astronomy. Hubble continues its legendary service despite decades in orbit. SPHERICS is mapping the entire sky. The challenge isn't building new capabilities, it's orchestrating the ones we have. And the orchestration for 3I Atlas is remarkable. JWST can pivot small fractions of its observing time toward the comet during key windows, using its unparalleled infrared sensitivity to dissect molecular emissions with unprecedented precision. Hubble adds its legendary resolution for morphology studies and size constraints. SPHERICS contributes wide-field spectral mapping that captures the extended environment around the nucleus. On the ground, the coordination extends across continents. Gemini North and South provide complementary observations from both hemispheres. Palomar Observatory adds its own perspective. Neue Lab coordinates across multiple facilities to ensure comprehensive coverage. But here's where it gets interesting. Some of the best observations might not come from Earth at all. Spacecraft scattered throughout the solar system find themselves in uniquely advantageous positions during 3I Atlas's passage. ESA's JUICE mission, fresh from its August 31st Venus gravity assist, will be approximately 68 million kilometers from the comet during key observation windows. NASA's Psyche spacecraft, en route to its metallic asteroid target, sits roughly 45 million kilometers away. Mars orbiters, including NASA's Mars Reconnaissance Orbiter, China's Tianwen-1, and the UAE's HOPE mission, enjoy front-row seats at distances of just 29 million kilometers. These aren't purpose-built comet missions. They're existing spacecraft with their own primary objectives, their own carefully planned timelines, their own scientific priorities. but geometry and timing have aligned to offer unprecedented opportunities for multi-platform observations of an interstellar visitor. The advantages of spacecraft observations become crucial around perihelion, when Earth's view of 3I Atlas becomes severely compromised by solar glare. While ground-based telescopes lose sight of the comet behind the Sun's overwhelming brightness, spacecraft positioned throughout the solar system maintain clear lines of sight. They can watch the comet's tail develop, monitor its outgassing behavior, and potentially even sample dust particles if orbital mechanics align favorably. These observations aren't guaranteed, they're opportunistic. Spacecraft instruments aren't necessarily optimized for comet science, and primary mission requirements take priority. But even modest resolution imaging and basic spectroscopy from these platforms could provide invaluable data about how 3I Atlas behaves when it's impossible to observe from Earth. The public engagement potential deserves recognition. Live-streamed observing sessions, particularly from major ground-based facilities like Gemini South, have proven enormously popular for previous interstellar visitors. Citizen science projects that allow the public to participate in data analysis add another layer of engagement. When the general public can directly contribute to cutting-edge science, it transforms abstract research into personal investment. Behind the scenes, 3I Atlas is driving technological improvements that will benefit all future astronomy. Moving targets require more sophisticated tracking algorithms. Faint objects demand better noise reduction techniques. Cross-facility coordination needs robust data-sharing protocols. Each of these challenges pushes the boundaries of what's technically possible, creating solutions that benefit far more than just comet science. The data tooling upgrades are particularly significant. Better pipelines for processing observations of moving targets will improve asteroid surveys, planetary mission operations, and space situational awareness. Enhanced cross-calibration between JWST, Spherix, and Hubble creates more reliable photometric standards for all astronomical observations. These aren't just improvements for this one comet, they're infrastructure upgrades for the entire field. Future mission concepts are already incorporating lessons learned from 3I Atlas observations. ESA's Comet Interceptor mission represents a new philosophy. Instead of launching toward a specific target, position a spacecraft at a gravitationally stable point and wait for interesting objects to announce themselves. 3I Atlas validates this approach by demonstrating both the scientific value of interstellar visitors and the practical challenges of late discovery and high velocity. The budget reality check is crucial here. This entire scientific windfall doesn't require congressional appropriations or multi-year development programs. It's primarily a matter of coordination, scheduling, and data sharing among existing facilities. The most expensive component might be the extra staff time needed to analyze the resulting datasets. That's not to minimize the complexity. Coordinating observations across multiple space agencies, ground-based facilities, and spacecraft missions requires diplomatic finesse and technical precision. Time on premier facilities like JWST and Hubble is extraordinarily valuable, allocated through competitive processes months or years in advance. Pivoting even small amounts of observing time toward 3I Atlas represents a significant commitment. But the return on investment is extraordinary. For relatively modest coordination costs, humanity gains its most comprehensive look yet at material from another star system. We develop new techniques for rapid response observations of transient targets. We demonstrate international cooperation in real-time science. We inspire the next generation of scientists and engineers. The lesson extends beyond this single comet. In an era of increasingly expensive flagship missions and decade-long development cycles, 3I Atlas demonstrates the continuing power of smart coordination among existing assets. Sometimes the most profound discoveries don't require the newest, biggest, most expensive tools. They require the wisdom to use what we have most effectively. As we watch this coordination unfold, we're witnessing a preview of how science will work in the era of routine interstellar visitors. The infrastructure is largely in place. The techniques are being refined. The international cooperation frameworks are being tested. 3I Atlas isn't just a comet, it's a proof of concept for 21st century astronomy. Part 4. C. Tier Outcome, the Quiet Pass. Not every cosmic visitor arrives with fanfare. Not every scientific breakthrough comes wrapped in spectacle and social media buzz. Sometimes the most profound discoveries happen quietly, methodically, without changing anyone's weekend plans or inspiring Hollywood blockbusters. This is the most likely scenario for 3I Atlas, and that's perfectly fine. The geometry of the situation works against dramatic visibility. When 3I Atlas reaches perihelion in late October 2025, Earth will be poorly positioned for observations. The comet will be lost in solar glare, invisible to casual observers, accessible only to specialized spacecraft and carefully planned professional observations. There will be no naked eye spectacle, no social media photos of a brilliant tail stretching across the sky, no reason for people to gather in parks with binoculars. Instead, there will be datasets. Lots of them. The observational cadence tells the story. Intense monitoring as the comet approaches, a solar conjunction gap when Earth-based observations become impossible, then resumed observations in December as 3I Atlas emerges from behind the sun's glare. This structure shapes what we learn and when we learn it, creating a natural progression from approach characterization to post-perihelion analysis. During the solar gap, spacecraft positioned throughout the solar system continue their work. Mars orbiters monitor the comet's behavior when it's closest to the Sunday deep space missions track its tail development. Solar observatories capture its interaction with the solar wind. The data collection never stops, it just shifts platforms. For most people, this will feel like a non-event. News coverage will be respectful but restrained. Scientists study distant comet, rather than death from space narrowly avoids Earth. Educational institutions will incorporate 3I Atlas into lesson plans about the solar system and scientific method. Space agencies will publish regular updates with measured language about scientific progress and international cooperation. This measured response represents healthy scientific communication. 3I Atlas is fascinating to scientists and genuinely important for our understanding of planetary formation, but it's not going to fundamentally alter daily life for anyone outside the astronomical community. The story is safe, distant, beautiful dataset, rather than once-in-a-lifetime sky event. The quiet nature of this outcome creates space for genuine scientific education. Without sensationalism or crisis framing, there's room to explain how uncertainty works in science, how preprints differ from peer-reviewed papers, why patience is essential to discovery. These are crucial lessons for scientific literacy, but they're often overwhelmed by more dramatic narratives. Consider the educational value of watching science work normally. The public can follow along as initial observations get refined, as preliminary results undergo peer review, as competing hypotheses get tested against new data. This is how science actually functions, not through sudden revelations or paradigm-shifting announcements, but through careful accumulation of evidence and gradual refinement of understanding. The professional community benefits enormously from this approach. Cross-validation between different instruments and facilities proceeds without external pressure. Negative results and non-detections get appropriate attention rather than being dismissed as boring. Long-term studies can develop without the distraction of constant public explanations and media management. From a policy perspective, the quiet outcome supports steady, sustainable funding for astronomical surveys rather than boom and bust cycles driven by public excitement. Programs like Atlas, Linear, and the upcoming Rubin Observatory need consistent support over decades to function effectively. Sensational events can trigger short-term funding increases, but they can also create unrealistic expectations about the pace and nature of discovery. The cultural impact, though subtle, may be more profound than immediate spectacle. 3i Atlas normalizes the idea that our solar system is not isolated, that material moves between star systems, that we live in a galactic neighborhood where visitors occasionally stop by. This represents a fundamental shift in how humanity thinks about its cosmic context, but it's the kind of shift that happens gradually, through accumulated awareness rather than sudden revelation. For astronomers, the quiet outcome allows focus on what matters most, the data. Without media circuses or public pressure for immediate results, research teams can take the time needed for proper calibration, thorough analysis, and careful interpretation. The resulting papers will be more reliable, more comprehensive, and more useful for future research. The long-term scientific value often exceeds the immediate impact. Datasets from 3i Atlas will be archived and reanalyzed for years to come as techniques improve and new questions arise. Today's preliminary results become tomorrow's refined measurements, which become next year's theoretical insights, which become next decade's textbook examples. This pattern repeats throughout astronomy. Many of the most important discoveries in the field were initially unremarkable, catalogued objects that became crucial years later when better analysis techniques revealed their significance. Pulsar timing arrays, gravitational wave detection, exoplanet discovery all followed this pattern of quiet accumulation, leading to revolutionary understanding. The international cooperation aspect continues regardless of public attention level. Scientists from different countries and institutions collaborate on data analysis, instrument calibration, and theoretical interpretation. These professional relationships strengthen the global scientific community and establish frameworks for future discoveries. Data sharing protocols developed for 3i Atlas will benefit other moving target observations. Rapid response coordination techniques will improve responses to future interstellar visitors. Cross-facility calibration methods will enhance all astronomical observations involving multiple telescopes. Even in the quiet scenario, citizen science opportunities remain available. Image processing projects, data validation tasks, and educational programs can engage interested members of the public without requiring mass participation or media attention. Quality over quantity often produces better results in citizen science contexts. The absence of drama doesn't mean absence of discovery. Some of the most significant advances in our understanding of planetary formation, stellar evolution, and galactic structure have come from careful analysis of unremarkable objects. 3i Atlas could easily fall into this category, scientifically crucial but publicly invisible. Perhaps most importantly, the quiet outcome allows 3i Atlas to establish baselines for future interstellar visitor studies. The observational techniques, analysis methods, and coordination protocols developed for this object will inform responses to future visitors when discovery timing, geometry, or characteristics might be more favorable for public engagement. The expectation versus reality gap matters here. Managing public expectations appropriately, emphasizing scientific value over visual spectacle, creates healthier relationships between professional astronomy and public understanding. Science communication works best when it's honest about what to expect and why it matters. In the end, the quiet pass scenario represents science at its best: careful, methodical, international, patient, and focused on understanding rather than entertainment. Not every cosmic event needs to be a blockbuster. Sometimes the most valuable discoveries happen when scientists can work without distraction, building knowledge step by careful step. The universe is full of quiet wonders. 3i Atlas may be one of them. Part 5. F-tier myths, cinematic worst, cases and why they're not on the table. Let's get the nightmares out of the way first, because in our age of social media panic and cinematic disaster fantasies, someone's going to ask, can 3I Atlas destroy Earth? Can it trigger solar flares? Can it somehow hide behind the sun and launch a surprise attack? The short answer is no. The long answer involves some very satisfying mathematics that demonstrates exactly why these fears are not just unlikely, but physically impossible. Start with the impact scenario, because that's usually everyone's first concern. 3I Atlas will approach no closer than approximately 1.6 astronomical units from Earth. That's roughly 270 million kilometers. To put this in perspective, this is farther than the distance between Earth and Mars at their closest approach. It's like worrying about a car accident when the other vehicle is in a different time zone. But let's be more precise about this. The gravitational influence of any object falls off as the inverse square of distance. At 270 million kilometers, 3I Atlas, even if it was somehow much larger and more massive than current observations suggest, would exert less gravitational pull on Earth than a large building exerts on you when you walk past it on the street. The gravitational chaos myth deserves special attention because it sounds almost scientific. Could 3I Atlas somehow disrupt planetary orbits or destabilize the solar system? The mathematics are brutal in their clarity. Even if 3I Atlas were 1,000 times more massive than current estimates suggest, its gravitational effect on planetary motion would be utterly negligible. Consider the mass ratios involved. Earth weighs approximately 6 times 10 to the 24th power kilograms. Jupiter weighs about 318 times more than Earth. The Sun weighs about 330,000 times more than Earth. 3I Atlas, generously assuming a 5-kilometer radius and typical comet density, weighs perhaps 10 to the 14 power kilograms. That means Earth outweighs 3I Atlas by roughly 60 billion to 1. The idea that this tiny iceberg could meaningfully perturb a planet is like suggesting that a mosquito could deflect a freight train by flying into it. The doomsday tail scenario requires its own mathematical reality check. Comet tails consist of incredibly tenuous gas and dust, far less dense than the best vacuum we can create in terrestrial laboratories. At astronomical distances, even passing directly through a comet tail poses no meaningful threat to spacecraft, let alone planets. The material is so diffuse that you could compress an entire comet tail into a sphere and it might weigh less than a car. Moreover, 3I Atlas won't come anywhere near Earth. Its tail, no matter how spectacular it might appear in photographs, consists of particles following slightly different trajectories than the nucleus itself. These particles will disperse across millions of kilometers of space, creating a beautiful but utterly harmless display for any spacecraft positioned to observe it. Now for the truly creative conspiracy. It's hiding behind the sun to attack. This myth demonstrates a fundamental misunderstanding of both orbital mechanics and the nature of the observations themselves. 3I Atlas isn't hiding. It's following a predictable trajectory calculated from hundreds of observations by dozens of facilities worldwide. The solar conjunction period, when Earth-based observations become difficult, is a consequence of geometry, not strategy. During this period, spacecraft positioned throughout the solar system will maintain clear lines of sight to the comet. Mars orbiters, deep space missions, and solar observatories will continue monitoring its behavior. There's no concealment, no surprise capability, no strategic positioning. There's just a comet following Newton's laws of motion with clockwork precision. The size mythology needs addressing too. Early media reports occasionally conflate brightness with size, suggesting that 3I Atlas might be much larger than current estimates indicate. But brightness depends on surface area, reflectivity, and outgassing activity, not just size. A small, highly active comet can appear brighter than a large, dormant one. Current observations constrain the nucleus to no more than about 5.6 kilometers across, and possibly much smaller. Even if 3I Atlas were larger than estimated, size alone doesn't create danger at these distances. A 10-kilometer comet at 270 million kilometers is still utterly harmless to Earth, like worrying about getting wet from a water balloon thrown from the next state over. Let's establish an evidence standard for the rest of our investigation. Peer-reviewed papers carry the most weight, followed by preprints that are undergoing review, followed by conference presentations and press releases. Extraordinary claims require extraordinary evidence, and the more extraordinary the claim, the higher the evidence bar should be. NASA's official communications about 3I Atlas consistently emphasize its safe distance and predictable behavior. These aren't bureaucratic cover-ups or attempts to prevent panic. They're accurate summaries of what the orbital mechanics actually show. When space agencies around the world agree on basic facts like trajectory and closest approach distance, those facts are extraordinarily reliable. The scientific community has developed sophisticated methods for detecting and characterizing potentially hazardous objects. The same surveys that found 3I Atlas routinely identify and track asteroids and comets that could pose genuine risks to Earth over timescales of centuries. These systems work, they're constantly improving, and they're operated by people whose careers depend on accuracy. Media literacy becomes crucial here. Headlines designed for clicks don't always reflect the content of the articles they introduce, and articles don't always accurately represent the scientific papers they discuss. The most reliable information comes directly from space agencies, major observatories, and the scientists actually conducting the observations. Visual effects in movies and television create unrealistic expectations about how space objects behave. Real comet tails are usually invisible to the naked eye, extend in directions determined by solar wind rather than orbital motion, and consist of material so tenuous that it barely qualifies as matter at all. Real asteroid impacts require very specific size and velocity combinations to cause significant damage. Real orbital mechanics follow predictable mathematical rules that don't allow for dramatic last-minute course changes or surprise attacks. The myth-busting isn't meant to dismiss curiosity or discourage questions. Healthy skepticism and scientific inquiry go hand in hand. But they work best when directed toward understanding what's actually happening rather than imagining what might be happening if the laws of physics worked differently. Here's our promise for the rest of this investigation. We'll clearly distinguish between peer-reviewed results, preliminary findings, and speculative possibilities. We'll show our work when we make claims about distances, masses, and energies. We'll acknowledge uncertainty when it exists and avoid certainty when it doesn't. 3I Atlas offers plenty of genuine mysteries worth exploring. We don't need to invent fictional dangers to make it interesting. The truth about this interstellar visitor is remarkable enough without embellishment, threatening enough to our preconceptions without being threatening to our planet. Part 6. Gravity, Tides, and Orbital Mechanics. Keep it real. Mathematics doesn't lie. It doesn't exaggerate for dramatic effect, doesn't hedge its bets for political reasons, and doesn't care about our hopes or fears. When we apply the cold, precise language of orbital mechanics to 3I Atlas, the story it tells is both reassuring and illuminating. Let's start with the fundamentals of what makes an orbit hyperbolic. Every orbit has an eccentricity, a number that describes how stretched or circular the path is. Circles have an eccentricity of 0. Ellipses have eccentricities between 0 and 1. Parabolas have an eccentricity of exactly 1, and hyperbolas, the mathematical curves that describe escape trajectories, have eccentricities greater than 1. 3I Atlas has an eccentricity of approximately 6. This is not a measurement uncertainty or a preliminary estimate subject to revision. This is a fundamental characteristic determined by hundreds of precise position measurements from multiple observatories worldwide. An eccentricity of 6 means the object is moving far too fast to be captured by the Sun's gravity. It came from interstellar space. It will return to interstellar space, and there's nothing in our solar system massive enough to change that fact. The velocity at infinity, the speed 3I Atlas would maintain if it were traveling through empty space far from any gravitational influences, is approximately 57 to 58 kilometers per second. This is its cosmic baseline speed, the velocity it carries as a relic of its formation and ejection from another star system. When combined with the Sun's gravitational influence, this velocity determines every aspect of 3I Atlas's trajectory through our solar system. That inbound trajectory traces back to the constellation Sagittarius, not because 3I Atlas originated there recently, but because that's the direction it was traveling when it entered the sphere of the Sun's gravitational influence. The actual journey from its birth star to our solar system likely took millions of years and involved a much more complex path through the galaxy's gravitational landscape. Here's where the mathematics become simultaneously elegant and reassuring. Once 3I Atlas entered our solar system, its entire future path became precisely predictable. Newton's laws of motion and gravity don't allow for surprises, course corrections, or dramatic last-minute changes. Every spacecraft navigation team in the world can calculate this trajectory to extraordinary precision using equations that haven't changed since the 17th century. The perihelion distance, 1.36 to 1.4 astronomical units, places 3I Atlas well outside Earth's orbit at its closest approach to the Sunday. That's roughly 204 million kilometers, or about 1.5 times the distance from Earth to the Sunday. Even if 3I Atlas were somehow equipped with rocket engines and guidance systems, which it emphatically is not, the energy required to alter its course enough to threaten Earth would be beyond anything humanity has ever built. Planetary deflections during the passage are real but minuscule. As 3I Atlas swings past the Sun, it will experience gravitational influences from Jupiter, Saturn, and the other planets. These influences will slightly modify its outbound trajectory, changing its direction by fractions of degrees and its speed by meters per second. But the fundamental character of the orbit remains unchanged: hyperbolic in, hyperbolic out. The closest approach to Earth occurs in mid-December 2025 at approximately 1.6 to 1.8 astronomical units, roughly 270 million kilometers. At this distance, 3I Atlas exerts less gravitational force on Earth than Earth exerts on the International Space Station. The tidal effects are so negligible they fall below the threshold of measurement by our most sensitive instruments. To understand why, consider the mathematics of tidal forces. These forces depend not just on mass and distance, but on the gradient of gravitational field strength. The Moon creates noticeable tides on Earth because it's relatively close and relatively massive. 3I Atlas, even at its closest approach, is nearly 700 times farther away than the Moon, and perhaps 1 trillion times less massive. Even if we wildly overestimate 3I Atlas's mass, imagining it somehow 10 times larger and denser than observations suggest, the tidal effects on Earth would still be immeasurably small. You would have more tidal influence on Earth by jumping up and down in your backyard than 3I Atlas has at its closest approach. The orbital inclination adds another layer of safety and predictability. 3I Atlas approaches the solar system at a high angle relative to the plane where Earth and the other planets orbit. This retrograde, high-inclination trajectory is actually typical for random interstellar objects, exactly what you'd expect from something that originated in a completely different stellar environment with no relationship to our solar system's formation. Could the Sun somehow capture it? This question reveals a fundamental misunderstanding of orbital energy. Capture requires removing exactly the right amount of kinetic energy at exactly the right moment. Natural capture is extraordinarily rare and requires very specific circumstances, usually involving multi-body gravitational interactions or atmospheric drag, neither of which applies to 3I Atlas. The escape energy dominates everything else. 3I Atlas carries enough kinetic energy relative to the Sun to escape the solar system, even if it started from rest at the Sun's surface. The planetary deflections it experiences are like trying to stop a freight train by throwing ping-pong balls at it, measurable in principle, irrelevant in practice. N-body simulations, computer models that track the gravitational influences of all the planets simultaneously, confirm these analytical predictions. When you run 3I Atlas's trajectory forward or backward through time, accounting for every planetary perturbation, the result is consistent: hyperbolic approach, brief solar system passage, hyperbolic departure. The historical context provides reassurance through familiarity. 1I/Oumuamua followed a similar hyperbolic trajectory during its 2017 visit. 2I/Borisov did the same in 2019 and 2020. The pattern is consistent. Interstellar objects visit, provide scientific opportunities, and depart without drama. But there's an important difference in public perception. Both previous interstellar visitors were discovered relatively late in their passages, when their trajectories were already well established and their departure was imminent. 3I Atlas was found earlier in its approach, providing more time for observations but also more time for speculation and misunderstanding. The flirtation with Mars, occasionally mentioned in early reports, deserves clarification. 3I Atlas's orbit does carry it through the general region of Mars's orbital distance, but Mars won't be anywhere near that location when the comet passes through. It's like saying two cars will collide because their routes cross the same intersection, ignoring the fact that they'll arrive hours apart. Even if Mars and 3I Atlas were to approach each other more closely, which they won't, the gravitational interaction would be insignificant. Mars has only 11% of Earth's mass and far less gravitational influence than Jupiter, which has already been accounted for in trajectory calculations. The mathematics of orbital mechanics leave no room for surprise disasters, hidden dangers, or last-minute plot twists. The laws of physics that govern 3I Atlas are the same ones that allow us to navigate spacecraft to distant planets, predict eclipses centuries in advance, and maintain GPS satellite constellations with meter-level accuracy. When scientists say 3I Atlas poses no threat to Earth, they're not making a guess or offering a professional opinion. They're stating a mathematical certainty based on fundamental physical laws that have been tested and verified countless times over centuries of scientific investigation. The real mystery isn't whether 3I Atlas is dangerous. It isn't. The real mystery is what this ancient traveler can teach us about how worlds form around other stars, what materials were common in the early galaxy, and how planetary systems across the cosmos build themselves from dust and gravity. Distance measurements in astronomical units and mass ratios expressed in scientific notation might seem abstract, but they represent the difference between rational assessment and irrational fear. 3I Atlas is fascinating because it's safe to study, not despite being safe to study. Part 7. Sunlight, Solar Wind, and the Coma. Picture an ancient iceberg, older than Earth itself, awakening after millions of years of deep freeze. As 3I Atlas draws closer to the Sun, something remarkable begins to happen. The sparse starlight that has warmed its surface for eons suddenly intensifies into the focused energy of our solar system's central furnace. This is the moment when a dark, frozen wanderer transforms into an active comet. The physics are elegantly simple. Sunlight carries energy, and that energy heats whatever it touches. As 3I Atlas approaches perihelion, solar heating penetrates its surface layers, causing frozen materials to sublimate, transforming directly from ice to vapor without passing through a liquid phase. This outgassing process creates the characteristic coma, the extended atmosphere of gas and dust that makes comets visible across vast distances. But 3I Atlas isn't following the typical script. Most comets in our solar system are dominated by water ice. When they approach the Sun, water sublimation creates the bulk of their coma and tail. Carbon dioxide, carbon monoxide, and other compounds contribute, but water usually takes the lead role in the outgassing drama. The James Webb Space Telescope revealed something different. 3I Atlas shows unusually strong carbon dioxide emissions compared to water, with early estimates suggesting a ratio approaching 8:1. This isn't just unusual, it's a complete inversion of what we normally see. The FEARX mission added another piece to the puzzle. Its wide-field spectral observations mapped the carbon dioxide coma extending for hundreds of thousands of kilometers, nearly the distance from Earth to the Moon. Meanwhile, water and carbon monoxide emissions that should announce themselves clearly in this spectral range were conspicuously absent. These are preliminary results, the kind that make scientists excited and nervous simultaneously. The teams analyzing this data are still refining their measurements, still double-checking their instruments, still making sure they're not seeing instrumental artifacts or calibration errors. But if these observations hold up under scrutiny, they're pointing towards something genuinely extraordinary. The carbon dioxide dominance suggests several possibilities, each with intriguing implications. Perhaps 3I Atlas formed in the outer reaches of its birth system, beyond the carbon dioxide ice line where carbon dioxide freezes before water does. This would place its origin in a region analogous to our outer asteroid belt or beyond, in the cold, dark zones where only the most volatile materials remain gaseous. Alternatively, 3I Atlas might have developed a surface crust that acts like a selective valve, allowing carbon dioxide to escape while trapping water beneath. Think of it as cosmic permafrost, an outer layer that insulates the interior and controls which materials can sublimate under solar heating. Both scenarios challenge our standard models of how outer protoplanetary disks distribute their chemical inventory. We're not just looking at one oddball comet, we're potentially glimpsing an entirely different approach to volatile chemistry in planetary formation. The dust production mechanics become particularly interesting when carbon dioxide leads the outgassing process. Water vapor has specific properties when it comes to lifting and accelerating dust particles away from a comet's nucleus. Carbon dioxide behaves differently, with different expansion rates, different cooling properties, different abilities to entrain solid particles. This means the tail morphology and brightness evolution of 3I Atlas might not follow familiar patterns. The dust distribution might be different, the particle size ranges might be unusual. The overall appearance in telescopic images might challenge expectations based on water-dominated comets. Visibility expectations need to be managed carefully here. Despite its chemical activity, 3I Atlas won't necessarily put on a spectacular show for casual observers. The geometry of its passage places it behind the Sun's glare during peak activity, making Earth-based observations challenging precisely when the comet is most active. This timing creates a natural experiment in comparative comet science. We can observe 3I Atlas during its approach, lose sight of it during solar conjunction, then pick up observations again as it recedes from the Sunday. The before and after comparison will reveal how perihelion passage affects its composition, outgassing rates, and dust production. Spacecraft positioned throughout the solar system fill the observation gap during solar conjunction. Mars orbiters can watch the comet's behavior when Earth-based telescopes are blinded by solar glare. This multi-platform approach provides unprecedented coverage of a comet's complete passage through the inner solar system. The comparison with typical solar system comets illuminates just how unusual 3I Atlas appears to be. Most comets show water emission lines dominating their spectra near 1 astronomical unit from the Sunday. They produce predictable ratios of different molecular species. They follow well-understood patterns of brightness variation and tail development. 3I Atlas seems to be writing its own rules. The grain size analysis from ongoing studies will reveal whether carbon dioxide-dominated outgassing produces different dust characteristics than water-dominated systems. Larger grains, smaller grains, different mineral compositions, unusual shapes, all of these factors could distinguish interstellar dust from solar system dust in ways we're only beginning to understand. Gas velocity measurements add another layer of complexity. Different molecular species sublimate at different rates and expand away from the nucleus at different speeds. Carbon dioxide has different thermodynamic properties than water, which could create different pressure gradients, different expansion patterns, different interactions with the solar wind. Fragmentation likelihood becomes a relevant concern as solar heating intensifies. Some comets break apart under thermal stress, especially if they have weak internal structure or contain materials with different expansion coefficients. 3I Atlas's unusual composition might make it more or less susceptible to fragmentation, a question that can only be answered through careful monitoring. The multiple apparitions across the solar conjunction gap will provide crucial data about temporal evolution. How does the comet's behavior change as it approaches perihelion? How does it respond to peak solar heating? How does its activity decline as it recedes toward interstellar space? The tri-panel imaging from JWST offers a template for understanding molecular distribution. Total flux shows overall activity level. The 4.3 micrometer channel highlights carbon dioxide emission. The 2.7 micrometer channel reveals water emission. The contrast between these channels tells the story of 3I Atlas's unusual chemistry. For public outreach, the carbon dioxide coat analogy helps explain why some comets behave differently than others. Just as different planets have different atmospheric compositions, different comets carry different chemical signatures that reflect their formation environments and evolutionary histories. The caveat about compositional ratios bears repeating. These measurements will be refined as peer review proceeds and analysis techniques improve. What we're seeing now represents the first draft of 3I Atlas's chemical story, not the final version. But even as preliminary results, these observations are reshaping our understanding of volatile chemistry in planetary formation. They suggest that the processes that build worlds around other stars can produce outcomes very different from our solar system's template. They hint that interstellar space might be populated by a diverse collection of chemical signatures, each telling a unique story about planetary formation under different conditions. The awakening of 3I Atlas under our Sun's influence isn't just about one comet's behavior. It's about the diversity of outcomes possible when gravity, chemistry, and time collaborate to build worlds around stars throughout the galaxy. Part 8. Can we go meet it? Realistic investigation paths. The romantic notion of launching a spacecraft to rendezvous with 3I Atlas captures our imagination, racing across the solar system to shake hands with a visitor from another star. Unfortunately, the mathematics of orbital mechanics and spacecraft engineering are less romantic than our ambitions. The brutal constraints are straightforward. 3I Atlas is moving at 57 kilometers per second relative to the Sunday. It was discovered in July 2025, giving us roughly 3 to 4 months before perihelion passage. Even our fastest spacecraft take years to reach the outer solar system, and that's when we can plan trajectories carefully and launch at optimal times. Building and launching a dedicated intercept mission would require capabilities that exist only in science fiction. We would need a spacecraft that could accelerate to unprecedented velocities, survive the radiation environment near the Sun, and somehow match course with an object moving faster than anything we've ever attempted to intercept. But here's the beautiful thing about modern space exploration. We don't need to build new missions to conduct extraordinary science. We just need to be clever about using the assets we already have positioned throughout the solar system. The geometry of 2025 creates some remarkable opportunities. Several major spacecraft find themselves in advantageous positions during 3I Atlas's passage, not through careful planning but through the fortunate alignment of mission timelines and orbital mechanics. ESA's JUICE mission, the Jupiter Icy Moons Explorer, completed its Venus gravity assist on August 31, 2025, placing it in an excellent position for 3I Atlas observations. At approximately 68 million kilometers from the comet during key observation windows, JUICE carries sophisticated cameras and spectrometers that could provide unprecedented close-up views of an interstellar visitor. NASA's Psyche spacecraft, en route to study a metallic asteroid, sits roughly 45 million kilometers from 3I Atlas during its passage. While Psyche's instruments are optimized for asteroid science rather than comet observations, they could still capture valuable data about the comet's activity and dust environment. Perhaps most intriguingly, the Mars Orbiter constellation finds itself perfectly positioned for 3I Atlas observations. NASA's Mars Reconnaissance Orbiter, China's Tianwen-1 mission, and the UAE's Hope Orbiter all enjoy front-row seats at distances of just 29 million kilometers from the comet. These aren't purpose-built comet missions. They're existing spacecraft with their own primary objectives, their own carefully planned observation schedules, their own scientific priorities. But the fortunate alignment of orbits creates opportunities for multi-platform observations that would have been impossible to plan deliberately. The advantages of spacecraft observations become crucial around perihelion, when Earth's view of 3I Atlas becomes severely compromised by solar glare. Ground-based telescopes lose their target behind the Sun's overwhelming brightness precisely when the comet is most active and most scientifically interesting. Spacecraft positioned throughout the solar system don't face this limitation. They can maintain clear lines of sight to 3I Atlas throughout its passage, watching the tail develop, monitoring outgassing behavior, and potentially sampling dust particles if orbital mechanics align favorably. The measurement possibilities depend on each spacecraft's instrument complement. Imaging systems can track morphological changes in the coma and tail. Spectrometers can analyze the chemical composition of outgassing materials. Dust detectors can characterize particle sizes and impact rates if the spacecraft happens to pass through extended dust environments. These observations aren't guaranteed, they're opportunistic. Spacecraft instruments aren't necessarily optimized for comet science, and primary mission requirements always take priority. Mission planners must balance the scientific value of 3I Atlas observations against the needs of the primary mission objectives. But even modest resolution imaging and basic spectroscopy from these platforms could provide invaluable data about how an interstellar comet behaves when it's impossible to observe from Earth. The heliophysics community offers additional observational platforms. The Solar and Heliospheric Observatory, the Parker Solar Probe, and the upcoming Punch mission all maintain specialized instruments designed to study the solar wind and space weather environment. These spacecraft could observe 3I Atlas's interaction with solar particles and magnetic fields, providing insights into how interstellar material responds to our Sun's influence. Risk management becomes a crucial consideration for any spacecraft observations. Direct fly-throughs of comet tails, while scientifically valuable, expose spacecraft to potential damage from high-velocity dust impacts. Mission planners must weigh scientific opportunity against hardware protection, especially for spacecraft with ongoing primary missions worth hundreds of millions of dollars. Passive sensing from safe distances offers the optimal balance of scientific value and operational safety. Spacecraft can observe 3I Atlas from thousands or tens of thousands of kilometers away, well outside any dust hazard zones, while still collecting scientifically valuable data. The data choreography requires careful coordination across multiple space agencies and mission teams, timing observations to complement each other, sharing data rapidly for cross-validation, coordinating instrument settings for maximum scientific return. All of these factors require diplomatic finesse and technical precision. Before and after comparisons become particularly valuable when combining Earth-based observations with spacecraft data. Ground telescopes can characterize 3I Atlas during its approach. Spacecraft fill the observation gap during solar conjunction. Ground telescopes resume monitoring as the comet emerges from behind the sun's glare. This coordinated approach provides unprecedented coverage of a comet's complete passage through the inner solar system, revealing how perihelion passage affects composition, activity levels, and dust production in ways that single-platform observations cannot match. Citizen engagement remains possible even without dedicated spacecraft missions. Public webcasts of observing sessions, real-time data sharing from professional observations, and citizen science projects for image processing and data analysis allow the public to participate directly in cutting-edge research. Ground-based facilities like Gemini Observatory and NOILAB have demonstrated the public appetite for live observing sessions during previous interstellar visitor passages. These events combine education with entertainment, allowing people worldwide to watch professional astronomers conduct real research in real time. The bottom line is both disappointing and encouraging. We can't launch a Hollywood-style intercept mission to 3I Atlas. The physics and timing simply don't work. But the clever coordination of existing spacecraft and ground-based facilities can provide scientifically rich observations that might be even more valuable than a single dedicated mission. This approach represents the future of space science in an era of routine interstellar visitors. Instead of building expensive bespoke missions for each target, we maintain a constellation of capable spacecraft and ground-based facilities that can rapidly pivot to study unexpected opportunities. 3I Atlas is testing this coordinated approach in real time, demonstrating whether distributed observation networks can match the scientific return of traditional flagship missions while maintaining the flexibility to respond to targets discovered with little advance warning. The results will inform how we prepare for the next interstellar visitor and the one after that, as these cosmic travelers transition from rare curiosities to routine scientific opportunities. Part 9. What it teaches us about other suns. Every piece of cosmic debris tells a story about where it came from, but 3I Atlas might be carrying one of the oldest stories ever delivered to our scientific instruments. The preliminary evidence suggests we're looking at material that predates Earth's formation, a geological sample from the galaxy's youth, when the universe was fundamentally different than it is today. The kinematic evidence is tantalizing but still under debate. Several analyses of 3I Atlas's motion through space suggest it originated in the Milky Way's thick disk, a population of older, metal-poor stars that formed during the galaxy's early history. If this interpretation holds up, we're examining material that's at least 7 billion years old, possibly much older. To understand why this matters, we need to think about how the galaxy builds itself over cosmic time. Stars form in waves, with different generations using different raw materials and following different patterns of chemical evolution. The thick disk represents stars that formed during cosmic noon, the peak era of star formation when the universe was roughly half its current age, and galaxies were busy assembling themselves from smaller components. But the kinematic story isn't settled. A competing analysis using data from the Gaia Space Telescope suggests 3I Atlas might have originated in the thin disk, a younger population of stars with near-solar metallicity, implying a more recent origin in a star system much like our own. This disagreement isn't a failure of science, it's science working as designed. Different teams using different analysis techniques and different datasets are testing each other's results, refining measurements, and gradually converging on the truth. The process takes time, but it produces reliable answers. The chemical composition adds crucial evidence to this cosmic detective story. The carbon dioxide-rich nature of 3I Atlas points toward formation beyond the carbon dioxide ice line in its parent star system, or under specific irradiation conditions that favor carbon dioxide retention over water ice preservation. These chemical signatures are like fingerprints from exoplanetary nurseries we'll never visit directly. When planetary systems form, they scatter leftover planetesimals, chunks of rock, metal, and ice, throughout interstellar space. These ejected building blocks carry chemical signatures that sample the materials available in their birth environments. The exoplanet connection deserves emphasis. Every interstellar comet represents a piece of a failed planet, a chunk of material that almost became part of a world, but was instead ejected during the chaotic early phases of planetary system formation. By studying these cosmic refugees, we're essentially conducting archaeology on exoplanetary formation processes. If 3I Atlas truly originated in the thick disk, the implications are staggering. We would be examining material that formed when the galaxy was younger, when heavy elements were less common, when the chemical inventory available for planet formation was significantly different from what we see today. This connects to fundamental questions about planetary formation across cosmic time. Did early planetary systems form differently because they had access to different materials? Were volatiles like water and carbon dioxide distributed differently in primordial disks? How has the efficiency of planet formation changed as the galaxy has evolved? The comparative interstellar object science is building a catalogue of diversity that challenges our solar system-centric assumptions. 2I/Borisov appeared water-rich and relatively normal. 1I/Oumuamua was so unusual that astronomers still debate whether it was a comet at all. 3I Atlas seems carbon dioxide-dominated and chemically distinct. This small sample already suggests that interstellar space contains a variety of chemical signatures, each reflecting different formation environments and evolutionary pathways. As our detection capabilities improve and more interstellar visitors are discovered, we're building a census of how planetary formation processes vary across different stellar environments. The discovery rate projections are encouraging. The upcoming Rubin Observatory is expected to find interstellar objects at rates ranging from roughly 1 per year to potentially dozens per year, depending on their actual population density and size distribution. This transition from rare curiosities to routine discoveries will revolutionize interstellar object science. With larger sample sizes, astronomers will be able to perform population studies, looking for correlations between chemical composition and kinematics, between size and activity level, between orbital characteristics and formation environment. Individual objects like 3I Atlas provide fascinating case studies, but population statistics reveal underlying physical processes. The thick disk hypothesis, if confirmed, opens a window into cosmic history that's otherwise inaccessible. We can study the oldest stars in our galaxy, but their surfaces don't preserve information about the conditions in which they formed billions of years ago. Comets like 3I Atlas might retain that chemical memory in their frozen interiors. This connects to broader questions about cosmic evolution. When did the first planetary systems form? How different were they from modern systems? What role did early planet formation play in chemical evolution of the galaxy? These questions require data from the earliest epochs of galactic history, and 3I Atlas might be providing exactly that. The preprint culture in astronomy means we can follow these debates in real time as they develop. Papers appear on arXiv before peer review, allowing the community to see preliminary results and begin responding with additional observations or alternative interpretations. This transparent process shows how scientific consensus develops gradually through competition between different ideas, but we need to be careful about preliminary results. The thick disk versus thin disk debate will likely continue for months or years as additional kinematic analyses are completed and chemical composition measurements are refined. Science communication requires clearly distinguishing between provisional findings and established results. The galaxy mapping context helps visualize what we're discussing. The Milky Way's structure includes several distinct components: a thin disk of young stars like the Sun, a thick disk of older stars formed during the galaxy's early assembly, a central bulge of ancient stars, and a spherical halo of the galaxy's oldest stellar populations. Each component represents a different era in galactic evolution, with different chemical compositions, different kinematics, and different histories of star and planet formation. If 3I Atlas originated in the thick disk, it's carrying information from an era when the galaxy was still actively growing through mergers with smaller galaxies. The confidence metrics that accompany these analyses deserve attention. Kinematic studies typically provide error bars and statistical significance measures that indicate how reliable the conclusions are. Understanding these uncertainties is crucial for evaluating competing claims about 3I Atlas's origin. The ultimate payoff extends beyond one comet's biography. If we can reliably determine the galactic origins of interstellar objects, we gain a new tool for studying galactic evolution, stellar populations, and the history of planet formation across cosmic time. 3I Atlas might be more than just a visitor from another star system. It might be a messenger from another era entirely, carrying news from the galaxy's youth about how worlds were built when the universe was fundamentally different than it is today. The question isn't just where 3I Atlas came from, but when, and what that timing reveals about the long history of planets, stars, and galaxies building themselves from cosmic dust. Part 10. What it means for us, near term. The discovery of 3I Atlas represents more than just another entry in the catalogue of interstellar visitors. It's a stress test of our scientific infrastructure, a validation of our survey capabilities, and a preview of how astronomy will function in the coming decade when such visitors transition from rare curiosities to routine discoveries. The survey upgrade pathway is already clear. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, will revolutionize our ability to detect and characterize interstellar objects. Current estimates suggest Rubin could find anywhere from one interstellar visitor per year to potentially dozens annually, depending on the actual population density and size distribution of these objects in interstellar space. This dramatic increase in discovery rate will transform interstellar object science from a field driven by individual case studies to one capable of population statistics and comparative analysis. Instead of examining each visitor as a unique specimen, we'll begin to see patterns, correlations, and systematic differences that reveal underlying physical processes. The pipeline maturity improvements are already visible. Atlas, the Catalina Sky Survey, and Linear have refined their algorithms for detecting objects with unusual motion characteristics. The rapid identification of 3I Atlas as potentially interstellar demonstrates how these systems have learned from previous discoveries like 1I/Oumuamua and 2I/Borisov. Future interstellar visitors will be flagged more quickly, characterized more efficiently, and studied more comprehensively than their predecessors. The learning curve from 3I Atlas will benefit every subsequent discovery, creating a cumulative improvement in our response capabilities. The planetary defense literacy angle deserves particular attention. 3I Atlas provides a perfect teaching moment about uncertainty, measurement precision, and the difference between unknown and dangerous. The object's safe distance and predictable trajectory demonstrate how astronomical calculations work and why they're reliable. This educational opportunity matters because planetary defense depends on public understanding and support. When genuinely hazardous objects are discovered in the future, the public's response will be shaped by their familiarity with how these calculations work and why scientists can make confident predictions about trajectories and impact risks. Mission planning philosophies are evolving in response to discoveries like 3I Atlas. ESA's Comet Interceptor mission represents a new approach. Instead of launching toward a specific target, position a spacecraft at a gravitationally stable Lagrange point and wait for interesting targets to announce themselves. This wait and pounce strategy could become the standard for studying unpredictable targets with short discovery lead times. The career and training implications ripple through the astronomical community. Graduate students and postdocs are gaining experience with rapid response observational campaigns, multi-facility coordination, and international collaboration under time pressure. These skills will be increasingly valuable as transient astronomy becomes more common across multiple subfields. 3I Atlas mobilizes research teams across dozens of institutions and facilities. Students learn to work with data from JWST, Hubble, Spherix, and ground-based telescopes simultaneously. They practice coordinating observations across time zones and organizational boundaries. They develop expertise in moving target tracking, spectroscopic analysis, and multi-wavelength data fusion. These experiences produce researchers who are comfortable with complexity, uncertainty, and collaboration, exactly the skills needed for 21st century astronomy. The public engagement spillover effects extend far beyond astronomy. Live telescope sessions, citizen science projects, and educational programs around 3I Atlas introduce people to scientific methodology, international cooperation, and the excitement of discovery. These experiences influence career choices, voting patterns, and public support for scientific research. Educational institutions are incorporating 3I Atlas into lesson plans about orbital mechanics, spectroscopy, and scientific methodology. Students learn to distinguish between preliminary results and peer-reviewed findings, between speculation and evidence-based conclusions, between media hype and scientific reality. The budget implications deserve realistic assessment. The scientific windfall from 3I Atlas doesn't require massive new expenditures or congressional appropriations. It primarily represents coordination and scheduling among existing facilities and missions. The most expensive component might be the additional staff time needed for data analysis and paper preparation. This efficiency demonstrates the value of maintaining diverse, capable scientific infrastructure. Instead of building specialized missions for each target of opportunity, we maintain a portfolio of capabilities that can rapidly pivot to study unexpected discoveries. The return on investment is extraordinary. The next decade roadmap is becoming clear. Improved surveys will detect interstellar objects earlier and more reliably. Better alert systems will notify the global community more quickly. Enhanced coordination protocols will maximize scientific return from limited observing opportunities. Eventually, interceptor missions positioned at strategic locations will provide close-up studies of the most interesting visitors. Each step builds on lessons learned from current discoveries. 3I Atlas provides crucial experience with the entire pipeline from detection to detailed characterization to scientific interpretation. The metric to track is response time, how quickly the community can move from discovery to initial characterization to detailed follow-up observations. 3I Atlas establishes a baseline for this metric that future discoveries should improve upon. Rapid response requires not just better instruments, but better coordination. Data sharing agreements, observing time allocation procedures, and international cooperation frameworks all need refinement based on real-world experience with objects like 3I Atlas. The infrastructure investments are largely invisible to the public, but crucial for scientific success. better computational resources for orbit determination, improved communication systems for coordinating observations, enhanced data archiving for long-term studies. These behind-the-scenes improvements determine whether discoveries like 3I Atlas become transformative science or missed opportunities. The competence development aspect deserves emphasis. The real outcome for humanity isn't dramatic sky shows or existential threats. It's the gradual development of systematic capabilities for understanding our cosmic environment. We're becoming better at detecting unexpected visitors, characterizing their properties, predicting their behavior, and learning from their compositions. This competence extends beyond interstellar visitors to potentially hazardous asteroids, solar system exploration, and space situational awareness. The techniques developed for 3I Atlas improve our ability to track and understand any small body moving through space. The international collaboration templates being established now will serve as models for future discoveries. When the next interstellar visitor arrives, or when a genuinely hazardous asteroid is discovered, the coordination mechanisms tested on 3I Atlas will provide proven frameworks for rapid, effective response. Perhaps most importantly, 3I Atlas normalizes the idea that our solar system exists within a larger galactic community. These visitors remind us that planetary formation occurs throughout the galaxy, that other star systems occasionally share their leftovers with us, and that our cosmic neighborhood is more dynamic and interconnected than previous generations realized. This shift in perspective, from cosmic isolation to galactic citizenship, may ultimately be 3I Atlas's most significant contribution to human understanding. We're not alone in space, not in the science fiction sense of alien civilizations, but in the deeper sense of participating in galaxy-wide processes of planetary formation and evolution. The systems we're building to study 3I Atlas prepare us for a future where such discoveries are routine, where interstellar archaeology becomes a standard astronomical discipline, and where humanity's understanding of planetary formation extends far beyond our own solar system's example. Part 11. The Artifact Hypothesis, clearly labeled speculation. Now we enter the realm of speculation, the territory where science fiction meets scientific methodology. Some researchers, blogs, and preprint servers have suggested that 3I Atlas might not be a natural comet at all. Could it be artificial? Could it represent technology from another civilization? Could it pose risks beyond simple gravitational mechanics? Let's examine these claims with the same rigorous skepticism we apply to any extraordinary assertion. The artifact hypothesis requires extraordinary evidence because it makes extraordinary claims. If 3I Atlas were artificial, constructed or modified by intelligent beings, it would represent the most significant discovery in human history. The implications would reshape our understanding not just of our cosmic environment, but of our place in the universe itself. So what evidence would convince scientists that 3I Atlas is artificial rather than natural? The checklist is demanding but clear. Non-gravitational accelerations that are inconsistent with normal outgassing would be a strong indicator. Natural comets experience slight course corrections as sublimating gases create rocket-like thrust, but these accelerations follow predictable patterns based on solar heating and rotation. Artificial objects might show accelerations that don't match these patterns. Engineered reflectance characteristics would provide another crucial signature. Natural comet surfaces are chaotic mixtures of ice, rock, and organic compounds with irregular shapes and random orientations. Artificial surfaces might show geometric patterns, unusual brightness variations, or reflectance spectra that don't match any known natural materials. Coherent radio emissions would be perhaps the most definitive evidence. Natural comets don't generate organized radio signals beyond thermal noise and occasional plasma interactions. Artificial objects, especially those designed for communication or navigation, might broadcast structured signals that stand out clearly against the cosmic background. Controlled maneuvers would provide unambiguous proof of artificial origin. Natural objects follow predictable trajectories determined by gravity and outgassing forces. Artificial objects might demonstrate course corrections, orbital adjustments, or trajectory changes that couldn't be explained by known physical processes. The current observational evidence for 3I Atlas shows none of these artificial signatures. JWST observations reveal classical molecular emission lines from carbon dioxide, consistent with normal cometary outgassing. The Hubble Space Telescope shows a typical teardrop-shaped dust coma that matches theoretical predictions for natural comets under solar heating. SphereX mapping reveals extended carbon dioxide envelopes that follow expected patterns for gas expansion in the vacuum of space. Radio telescopes have monitored 3I Atlas for any unusual emissions. The searches have revealed thermal radiation consistent with a cold object warming under solar heating, but no structured signals, no coherent transmissions, no evidence of artificial radioactivity. Astrometric measurements, precise tracking of the object's position over time, show trajectory changes consistent with natural outgassing forces. The slight accelerations observed match theoretical predictions for carbon dioxide sublimation from a rotating nucleus. There's no evidence of controlled maneuvers or artificial course corrections. The media literacy component becomes crucial when evaluating artifact claims. Provocative blog posts and speculative articles spread faster through social media than careful scientific analysis. The attention-grabbing headline, "Could interstellar visitor be alien probe?" generates more clicks than spectroscopic analysis confirms natural comet composition. This isn't a conspiracy or cover-up, it's the natural consequence of how information spreads in the internet age. Sensational possibilities travel faster than mundane realities, regardless of their scientific merit. The dark forest hypothesis, popularized by science fiction author Liu Cixin, suggests that hostile civilizations might send artificial objects to scout or attack other worlds. This makes for compelling storytelling, but it requires evidence beyond the realm of current observations. Science fiction scenarios are worth considering as thought experiments, but they belong in the entertainment category until evidence elevates them to scientific hypotheses. There's nothing wrong with speculation as long as it's clearly labeled as such and doesn't masquerade as established fact. How would the scientific community test artificial origin hypotheses if evidence emerged? The protocols are already in place. Radio SETI organizations maintain arrays specifically designed to detect artificial signals. Radar installations can probe objects for unusual structural characteristics. Precise astrometry can detect controlled maneuvers that violate natural orbital mechanics. The thresholds for changing scientific consensus about 3I Atlas are high but achievable. A single unexplained radio signal might trigger additional observations but wouldn't constitute proof. Multiple independent detections of structured transmissions, confirmed by different facilities using different techniques, would be much more convincing. Similarly, one anomalous trajectory measurement might indicate instrumental error or unknown outgassing behavior. A pattern of controlled maneuvers observed by multiple tracking stations over extended periods would be much harder to explain through natural processes. The evidence ladder provides a framework for evaluating extraordinary claims. Rumors and speculation occupy the bottom rung. Preprint papers that haven't undergone peer review represent preliminary findings that might or might not survive scrutiny. Peer-reviewed papers that have survived expert examination carry much more weight. Scientific consensus emerges when multiple independent research groups reach similar conclusions using different methods. 3I Atlas artifact claims currently occupy the bottom rungs of this ladder. They represent speculation and preliminary suggestions rather than established scientific findings. The Oumuamua case study provides historical context for how these debates evolve. When 1I/Oumuamua was discovered in 2017, its unusual elongated shape and slight non-gravitational acceleration prompted speculation about artificial origin. Some researchers suggested it might be a solar sail or probe from another civilization. Over time, additional observations and theoretical work provided natural explanations for Oumuamua's unusual characteristics. The current scientific consensus favors natural origin, though some uncertainty remains about the specific mechanisms responsible for its behavior. This pattern, initial speculation followed by gradual convergence toward natural explanations, reflects how science processes extraordinary claims. The system is designed to be skeptical of dramatic assertions while remaining open to genuine evidence when it appears. The guardrail against ridicule deserves emphasis. Curiosity about artificial origins isn't inherently unscientific. SETI research, technosignature studies, and searches for evidence of technological civilizations represent legitimate scientific disciplines. The key is channeling curiosity into testable predictions rather than unfounded assertions. Good science distinguishes between "we don't have evidence for this" and "this is impossible." The absence of evidence for artificial origin doesn't prove 3I Atlas is natural, it just means the artifact hypothesis lacks supporting data. If compelling evidence of artificial origin did emerge, and to be clear, current observations strongly suggest it won't, the implications would be epochal. Contact with extraterrestrial technology would fundamentally alter human civilization's understanding of its cosmic context. The discovery protocols for such a scenario already exist. The International Academy of Astronautics maintains guidelines for announcing potential extraterrestrial contact. The scientific community has procedures for verification, confirmation, and public communication of extraordinary discoveries. But extraordinary claims require extraordinary evidence, and that evidence simply doesn't exist for 3I Atlas. Every observation to date supports natural comet origin. The chemical signatures, physical behavior, and trajectory characteristics all match theoretical predictions for interstellar comets. The outcome framing helps maintain perspective. If artifact evidence somehow emerged, which current data strongly argues against, it would indeed be the most significant discovery in human history. Absent such evidence, 3I Atlas remains a scientifically treasured comet that's expanding our understanding of planetary formation processes across the galaxy. The speculation serves a useful purpose by highlighting the importance of evidence-based reasoning and the scientific method. By examining what evidence would be required to support extraordinary claims, we better understand how science distinguishes between wishful thinking and reliable knowledge. 3I Atlas offers plenty of genuine mysteries worth exploring without invoking artificial origins. Its unusual chemical composition, ancient age, and interstellar journey provide more than enough scientific interest to justify careful study. The artifact hypothesis reminds us that the universe is full of possibilities we haven't yet discovered. But it also reminds us that distinguishing between possibilities and actualities requires careful observation, rigorous analysis, and healthy skepticism about claims that seem too extraordinary to be true. Part 12. Hidden Message Tropes, Myth-Busting Lab. In the age of social media and conspiracy theories, every unusual celestial event becomes a canvas for elaborate speculation. 3I Atlas, with its mysterious origin and unusual composition, has attracted its share of creative interpretations. Let's examine some of the more persistent claims and see how they hold up against actual evidence. The radio signals from the comet narrative represents perhaps the most common type of misinterpretation. Several social media posts have claimed that 3i Atlas is broadcasting structured radio transmissions, potentially indicating artificial intelligence or alien communication attempts. The reality is more mundane but also more interesting from a scientific perspective. Radio telescopes have indeed observed 3i Atlas, but they detect only thermal radiation, the natural radio emissions that any cold object produces when warmed by solar heating. These emissions follow predictable patterns based on the object's temperature, composition, and rotation rate. The sensitivity limits of current radio observations are well understood. If 3i Atlas were broadcasting at the power levels typical of human technology, our radio telescopes would easily detect such signals. The absence of structured emissions doesn't prove that artificial signals are impossible. It demonstrates that none exist at detectable power levels. Thermal noise considerations matter here. Space is filled with natural radio emissions from stars, galaxies, and cosmic ray interactions. Any artificial signal would need to stand out clearly against this background radiation. Pattern recognition algorithms, specifically designed to identify structured signals, have found nothing unusual in 3i Atlas observations. Beam shape analysis adds another layer of technical sophistication to radio searches. Natural thermal emissions spread equally in all directions, while artificial transmissions often show directional preferences. The radio emissions from 3i Atlas show the isotropic characteristics expected from natural thermal radiation. The geometric paths and numerology category of claims deserves special attention because it sounds almost scientific. Some online discussions have suggested that 3i Atlas's orbital parameters contain hidden mathematical relationships or deliberately chosen geometric patterns that indicate intelligent design. These claims misunderstand how orbital mechanics actually works. 3i Atlas's trajectory results from gravitational interactions with the Sun and planets, following Newton's laws of motion with exacting precision. The orbital elements, eccentricity, inclination, perihelion distance, are determined by the object's velocity and position when it entered the solar system, not by any conscious design process. Hyperbolic orbits for interstellar objects are mathematically inevitable given their high velocities relative to the Sunday. The specific parameters of 3i Atlas's orbit result from the random direction and speed it carried from its parent star system, modified by billions of years of galactic dynamics. The timed to hide at perihelion conspiracy theory misrepresents the geometry of solar system observations. 3i Atlas isn't hiding behind the Sun. It's following a predictable trajectory that happens to place it in solar conjunction during late October 2025. This timing is determined by orbital mechanics, not strategic planning. The comet's approach trajectory and Earth's orbital position combine to create the observation geometry. Spacecraft positioned throughout the solar system will maintain clear views of 3i Atlas during the conjunction period, providing continuous monitoring capabilities. Solar conjunction is a common occurrence for objects orbiting the Sunday. Mars experiences superior conjunction approximately every 26 months. Venus goes through conjunction phases regularly. These geometric alignments are natural consequences of orbital motion, not evidence of concealment attempts. The reproducible verification methods are crucial for evaluating these claims. Anyone can track updates on NASA's official 3i Atlas webpage, which provides regular updates on orbital parameters, observation schedules, and scientific results. ESA maintains similar resources for JWST observations and European spacecraft monitoring. Date stamps and version tracking allow interested parties to see how measurements evolve as more observations become available. Initial orbital estimates get refined as the observation arc lengthens. Preliminary composition measurements get updated as spectroscopic analysis improves. This transparent process demonstrates how scientific knowledge develops through accumulated evidence. Open data policies ensure that interested researchers worldwide can access the raw observations. Hubble Space Telescope images become publicly available through the Space Telescope Science Institute archives. NOILAB press releases include both processed images and technical details about observation methods. JWST spectra and analysis results are shared through the Space Telescope European Coordinating Facility. The claim versus check methodology provides a template for evaluating extraordinary assertions. When someone claims that 3i Atlas shows unusual behavior, interested parties can check current NASA updates, compare with official orbital predictions, and verify whether observations match the claims. URL verification helps distinguish between reliable sources and speculative websites. NASA, ESA, and major observatories maintain official domains with consistent formatting and citation practices. These sources provide technical details, error bars, and acknowledgements of uncertainty where appropriate. Scientific uncertainty requires careful communication. Preprints posted to arXiv represent preliminary research that hasn't undergone peer review. These papers can contain valuable insights but may also include errors or interpretations that don't survive expert scrutiny. The arXiv identifier system allows tracking of paper versions and subsequent publications in peer-reviewed journals. The peer review process serves as quality control for scientific claims. Papers accepted by journals like Astronomy, Astrophysics, the Astrophysical Journal, or Nature have survived expert examination by researchers familiar with the relevant analysis techniques and observational methods. Reading spectroscopic data requires some technical background, but follows consistent principles. The 4.3 micrometer spectral line indicates carbon dioxide emission. The 2.7 micrometer region reveals water vapor. The relative strengths of these features tell the story of 3i Atlas's unusual composition. Detection versus non-detection distinctions matter enormously in spectroscopic analysis. A clear spectral line at the expected wavelength constitutes positive detection. Noise at that wavelength, or signal levels below instrumental sensitivity, represents non-detection rather than evidence for absence. The live observing session invitations provide opportunities for public engagement with actual research. Major observatories occasionally offer webcasts during significant observations, allowing viewers to watch professional astronomers conduct real research in real time. These sessions demonstrate the methodical, careful nature of astronomical observation. Image release schedules follow predictable patterns for major facilities. Hubble typically processes and releases significant images within days or weeks of observation. JWST follows similar timelines for high-priority targets. Ground-based observatories often provide same-night availability for exceptional events. Comparison exercises help develop critical thinking skills. By examining multiple interpretations of the same data, viewers learn to distinguish between evidence-based conclusions and speculative extrapolations. Scientific literacy develops through practice in evaluating competing claims against available evidence. The educational value of myth-busting extends beyond 3i Atlas to general scientific literacy. Learning to identify reliable sources, understand uncertainty, quantification, and distinguish between correlation and causation provides tools for evaluating all kinds of technical claims. The invitation to direct participation concludes our myth-busting session. Rather than simply accepting or rejecting claims about 3i Atlas, interested parties can engage directly with the observational process. They can follow along with live observing sessions, examine archived data, and compare their interpretations with expert analysis. This participatory approach transforms passive consumers of science news into active participants in the scientific process. The tools exist, the data are available, and the methods are transparent. The only requirement is the willingness to engage with evidence rather than speculation. 3i Atlas offers genuine scientific mysteries worth exploring through careful observation and rigorous analysis. The hidden message we should take from this cosmic visitor isn't encoded in radio signals or geometric conspiracies. It's written in spectral lines and orbital mechanics that reveal the authentic story of an ancient traveler from another star. Part 13. Mars Rendezvous Fantasies and Why They Don't Pencil Out. The human imagination, when confronted with cosmic visitors, tends toward the grandiose. Social media buzzes with elaborate scenarios. Redirect 3i Atlas to seed Mars with water and organic compounds, use gravitational assists to crash it into Mars and thicken the atmosphere, fragment it into a ring system that could transform the red planet's climate. These ideas capture our desire to play cosmic engineer, but they founder on the unforgiving mathematics of orbital mechanics and spacecraft engineering. Let's start with the energy requirements, because energy is the universal currency that determines what's possible and what's fantasy in space operations. 3i Atlas is traveling at approximately 57 kilometers per second relative to the Sunday. This represents an enormous amount of kinetic energy, roughly 10 to the 21st power joules if we assume a conservative nucleus mass estimate. For comparison, the total energy output of all human civilization in a year is about 6 times 10 to the 20 power joules. Redirecting 3i Atlas would require changing its velocity by tens of kilometers per second, a delta V requirement that exceeds anything humanity has ever attempted by orders of magnitude. Our most powerful rockets can barely achieve delta V values of 15 to 20 kilometers per second from Earth's surface, and that's when starting from rest, not when trying to alter the trajectory of an object already moving at interstellar speeds. The timing constraints make these scenarios even more impossible. 3i Atlas was discovered in July 2025, providing roughly 3 to 4 months before perihelion passage. Even if we possess technology capable of delivering the required energy, which we emphatically do not, there wouldn't be enough time to design, build, launch, and intercept the comet. Previous spacecraft missions to comets have required years of careful planning and precise trajectory calculations. Deep Impact took 6 years from conception to asteroid impact. Rosetta took 10 years to reach comet 67P/Churyumov-Gerasimenko. These missions targeted predictable, slow-moving objects in the outer solar system, not high-speed interstellar visitors discovered months before closest approach. The mass reality check provides another dose of sobering mathematics. Even generously assuming 3i Atlas has a 5-kilometer radius and typical comet density, its total mass would be roughly 10 to the 14th power kilograms. This sounds massive in human terms, but it's utterly negligible compared to planetary scales. Mars has a mass of about 6.4 times 10 to the 23rd power kilograms, roughly 6 billion times more massive than our generous estimate for 3i Atlas. The gravitational influence of such a small object on a planet would be so minimal as to be unmeasurable even by our most sensitive instruments. The atmospheric seeding fantasy assumes that crashing 3i Atlas into Mars would somehow thicken the atmosphere or provide useful quantities of water and organic compounds. But the mathematics are unforgiving here too. Mars's atmosphere has a mass of roughly 2.5 times 10 to the 16 power kilograms. Even if 3i Atlas were pure carbon dioxide, which it isn't, and even if all of its mass could somehow be converted to atmospheric gas, which it couldn't, the atmospheric mass increase would be less than 1%. The water delivery scenario fares no better. Mars already contains substantial water reserves in its polar ice caps and subsurface deposits. The amount of water that might be contained in 3i Atlas's nucleus, even assuming optimistic estimates, would represent a tiny fraction of Mars's existing water inventory. The ring system proposal demonstrates a fundamental misunderstanding of how planetary rings form and persist. Saturn's rings exist because they're composed of countless small particles in stable orbits within the planet's gravitational influence. Creating artificial rings around Mars would require not just fragmenting 3I Atlas, itself a monumental engineering challenge, but also precisely placing those fragments in stable orbits with appropriate spacing and dynamics. Moreover, ring systems don't significantly affect planetary climates. Saturn's rings, despite their spectacular appearance, have negligible influence on the planet's atmospheric dynamics or energy balance. Mars rings created from 3I Atlas fragments would be beautiful but climatologically irrelevant. The gravitational assist scenarios reveal another layer of impracticality. Some proposals suggest using Mars's gravity to redirect 3I Atlas towards specific targets or trajectories. But gravitational assists work by exchanging momentum between spacecraft and planets, and the momentum exchange depends on the relative masses involved. Mars could indeed slightly deflect 3I Atlas's trajectory through gravitational interaction, but the effect would be measured in meters per second, not kilometers per second. The fundamental hyperbolic character of the orbit would remain unchanged. 3I Atlas would still escape the solar system, just along a slightly different trajectory. The Mars orbiter science opportunities, however, are genuinely realistic and scientifically valuable. NASA's Mars Reconnaissance Orbiter, China's Tianwen-1, and the UAE's HOPE mission will be excellently positioned to observe 3I Atlas from distances of roughly 29 million kilometers during its passage. These spacecraft carry sophisticated cameras, spectrometers, and other instruments originally designed for Mars observation that could provide unprecedented views of an interstellar visitor. The observations would be scientifically valuable without requiring any redirection, manipulation, or engineering intervention. The sci-fi storyboard versus real constraints comparison illustrates the gap between imagination and possibility. Science fiction scenarios typically ignore energy requirements, timing constraints, and engineering limitations that dominate real space operations. They assume technologies that don't exist and capabilities that violate fundamental physics. Real space missions succeed through careful planning, conservative engineering, and realistic goal setting. The most spectacular achievements, landing rovers on Mars, flying helicopters on alien worlds, taking pictures of black holes, result from decades of methodical development and incremental progress, not sudden technological breakthroughs or massive energy deployments. Historical precedent supports this reality check. Previous proposals for dramatic redirections of asteroids and comets have consistently failed feasibility analysis. The energy requirements exceed available technology by factors of thousands or millions. The timing constraints are incompatible with human development cycles. The engineering challenges multiply beyond any reasonable solution. 1I/Oumuamua generated similar grand proposals during its 2017 visit. None proved technically feasible within the constraints of discovery timing and available technology. 2I/Borisov inspired comparable speculation during its 2019 to 2020 passage. Again, the practical limitations overwhelmed the ambitious concepts. Opportunity cost considerations matter for actual spacecraft observations. Even modest redirection attempts would consume enormous resources and likely interfere with the primary missions of spacecraft that could otherwise conduct valuable scientific observations. Mars orbiters have carefully planned observation schedules designed to maximize scientific return from their primary missions. Diverting instrument time and operational resources toward 3I Atlas represents a trade-off that mission planners must evaluate against other scientific priorities. The back-of-the-envelope delta-V calculation that viewers can perform themselves demonstrates the scale of these energy challenges. Delta V equals the natural logarithm of the mass ratio times the exhaust velocity. Changing 3I Atlas's velocity by even 10 kilometers per second would require exhaust masses many times larger than the comet itself. This calculation assumes perfect efficiency and ignores practical constraints like propulsion system mass, structural limitations, and guidance requirements. Real spacecraft redirection would require even more energy than these theoretical minimums suggest. The fantasy sequence conclusion acknowledges that these grand scenarios make entertaining thought experiments while remaining physically impossible. There's value in imagination and speculation as long as they're clearly distinguished from realistic engineering assessments. The return to practical science offers more satisfying and achievable goals. Understanding 3I Atlas's composition, tracking its outgassing behavior, and learning from its chemical signatures provide genuine scientific advancement without requiring impossible engineering feats. The universe provides enough authentic wonders and genuine scientific opportunities that we don't need to invent fictional capabilities to make them interesting. Part 14. Sun. Triggered catastrophes. Why a tiny comet can't wake the sun. Fear has a peculiar relationship with scale. A tiny spider can terrify someone who remains calm during thunderstorms. A small asteroid can inspire panic, while massive hurricanes are treated as routine weather. 3I Atlas, despite its genuinely insignificant size compared to the Sun, has sparked concerns about triggering solar flares, coronal mass ejections, or other solar catastrophes that could threaten Earth. These fears misunderstand the Sun's fundamental nature and the energy scales involved in solar activity. The Sun is a massive, self-sustaining nuclear fusion reactor with a mass of approximately 2 × 10 to the 30th power kilograms. It generates energy through hydrogen fusion at its core, producing roughly 4 × 10 to the 26th power watts of power continuously. This energy output has remained remarkably stable for billions of years, varying by less than 1% over timescales relevant to human civilization. Solar flares and coronal mass ejections result from complex magnetic field interactions within the Sun's atmosphere. These phenomena involve magnetic energy storage and release processes that operate on scales vastly larger than any small comet could influence. The energy comparison reveals the absurdity of sun-triggering scenarios. A typical large solar flare releases roughly 10 to the 25th power joules of energy, about 6 times more energy than all of human civilization produces in a year. The total kinetic energy of 3I Atlas, moving at 57 kilometers per second, is roughly 10 to the 21st power joules, assuming generous mass estimates. This means that a single solar flare releases 10,000 times more energy than 3I Atlas carries in its entire motion. The comet is like a firefly trying to influence a volcanic eruption. The scales are so mismatched that meaningful interaction is impossible. The magnetic field consideration adds another layer of physical impossibility. Solar flares result from magnetic field line reconnection events in the Sun's corona. These magnetic fields are generated by the Sun's internal dynamo processes and shaped by plasma flows within the solar atmosphere. 3I Atlas has no significant magnetic field of its own and carries no mechanism for injecting magnetic flux into the solar system. Cometary material consists primarily of ice, rock, and organic compounds, none of which can meaningfully interact with the Sun's magnetic field structure. The distance factors make solar influence even more implausible. 3I Atlas reaches perihelion at approximately 1.4 astronomical units, roughly 210 million kilometers from the Sun's surface. At this distance, the comet subtends an angular size smaller than a pixel in most solar observations. The Sun's corona extends millions of kilometers into space, but even the most generous estimates of coronal extent don't reach anywhere near 3I Atlas's closest approach distance. The comet passes through interplanetary space, not through any component of the Sun's atmospheric structure. Correlation versus causation represents a crucial distinction that's often misunderstood in discussions of comet-solar activity relationships. Comets frequently appear in solar observatory images, particularly those taken by the Solar and Heliospheric Observatory, which maintains a constant watch on the Sun's environment. These appearances create visual associations between comets and solar activity that have no causal foundation. When a comet appears in a SOHO image on the same day that a solar flare occurs, the timing is purely coincidental. The two events are unrelated phenomena that happen to be captured by the same instrument. The SOHO database contains thousands of comet observations spanning more than 2 decades of solar monitoring. Statistical analysis of this database shows no correlation between comet passages and increased solar activity. If comets triggered solar flares, this correlation would be clearly visible in the data. The energy injection mechanism provides the most fundamental objection to sun-triggering scenarios. There is no known physical process by which a small comet could inject sufficient energy into the Sun to trigger flares or coronal mass ejections. Gravitational energy is negligible. 3I Atlas's gravitational influence on the Sun is orders of magnitude smaller than the tidal effects of Jupiter, which also don't trigger solar activity. Kinetic energy transfer would require direct impact, but 3I Atlas passes nowhere near the Sun's surface. Material injection through cometary outgassing faces similar problems. The few tons of gas and dust that 3I Atlas releases during its passage represent an utterly trivial addition to the Sun's environment, which processes billions of tons of material through its solar wind every second. The safety assessment for Earth reinforces the lack of connection between 3I Atlas and solar hazards. Earth maintains a safe distance of over 270 million kilometers from the comet at closest approach. Solar storm risks remain at normal background levels, determined by the Sun's natural 11-year activity cycle rather than any comet influence. Space weather monitoring systems operated by NASA, NOAA, and international partners maintain constant surveillance of solar activity. These systems can predict and track genuine solar storms that might affect satellite operations, power grids, and communication systems. None of these monitoring systems have identified any increased risk associated with 3I Atlas. The coronagraph illusion deserves special attention because it creates compelling but misleading imagery. Solar coronagraphs use occulting disks to block the Sun's bright surface, revealing the much fainter corona and any objects moving through the field of view. When comets appear in these images, they often seem to be interacting directly with the Sun because they're visible in the same frame. The visual impression suggests proximity and interaction, but the reality is that comets are typically millions of kilometers away from the Sun's surface, well outside any region where meaningful interaction could occur. The dramatic appearance of comets in coronagraph images results from the instrument's design rather than actual proximity to solar phenomena. The occulting disk creates an artificial night sky that makes faint objects visible against the dark background, creating spectacular imagery that can mislead casual viewers about the actual spatial relationships involved. Heliophysics expert perspectives uniformly dismiss comet-triggered solar activity scenarios. Researchers who study solar-terrestrial interactions, coronal physics, and space weather have found no credible mechanism by which small comets could influence solar behavior. The scientific literature contains thousands of papers on solar flare triggers, coronal mass ejection initiation, and magnetic field reconnection processes. None identify comets as significant factors in solar activity. The consensus among experts is clear. Comets are passive observers of solar behavior, not active participants. The educational value of addressing these misconceptions extends beyond 3I Atlas to general scientific literacy about energy scales, cause and effect relationships, and the importance of quantitative analysis in evaluating extraordinary claims. Understanding why 3I Atlas can't trigger solar catastrophes helps develop intuition about astronomical scale and the relative insignificance of small objects in cosmic environments. These concepts apply broadly to other astronomical phenomena and help distinguish between genuine risks and imaginary threats. The SOHO viewing recommendation stands despite the absence of actual solar interaction. The Solar and Heliospheric Observatory and other solar monitoring spacecraft will capture beautiful images of 3I Atlas passing through their fields of view during perihelion passage. These images will be scientifically valuable for studying comet tail development and dust distribution, educationally fascinating for demonstrating orbital mechanics, and aesthetically spectacular for their sheer visual appeal. They represent genuine astronomical photography at its finest, even though they document separate phenomena rather than interacting systems. The conclusion remains that awe without apocalypse provides more than enough inspiration for genuine appreciation of cosmic phenomena. 3I Atlas offers authentic scientific wonder without requiring fictional disasters to make it interesting. Part 15. The Long Afterglow, Culture and Science. Every great cosmic event casts two shadows, one brief and dramatic across the immediate moment, another long and subtle across the generations that follow. 3I Atlas, like every significant celestial visitor before it, will leave traces in both scientific archives and cultural memory that persist long after the object itself has disappeared into interstellar darkness. The cultural metamorphosis follows predictable patterns that have repeated throughout human history. Halley's Comet became a harbinger of political upheaval and divine judgment. The Tunguska event spawned a century of speculation about alien visitation and natural catastrophes. 1I/Oumuamua inspired both rigorous scientific analysis and elaborate science fiction scenarios about interstellar probes and artificial artifacts. 3I Atlas joins this tradition of cosmic visitors that capture human imagination and refuse to be constrained by mere scientific interpretation. Artists will paint its tail against starfields. Science fiction writers will imagine alien civilizations launching it toward Earth with hidden purposes. Internet communities will develop elaborate theories about its true nature that persist long after peer-reviewed papers settle the scientific questions. This cultural appropriation isn't a failure of science communication, it's an inevitable consequence of how human minds process wonder and uncertainty. Comets become symbols because they represent the vast unknown, the possibility that our assumptions about cosmic order might be wrong, the tantalizing suggestion that we're not alone in the universe. The scientific afterglow follows different patterns but promises longer-lasting impact. Archives mature over time as calibration techniques improve and analysis methods become more sophisticated. Today's preliminary spectral measurements will become tomorrow's definitive compositional analysis. Current orbital calculations will be refined to extraordinary precision. Initial hypotheses about formation environment will evolve into detailed models of interstellar chemistry. This maturation process operates on timescales measured in decades rather than months. The Hubble Space Telescope data, that seems definitive today, will be reanalyzed years from now using techniques that don't yet exist. JWST spectra that represent current state-of-the-art will be superseded by improved calibrations and better understanding of instrumental systematics. The thick disk versus thin disk origin debate exemplifies how astronomical controversies develop over extended timescales. Current kinematic analyses suggest different conclusions about 3I Atlas's galactic birthplace, but these disagreements will be resolved through accumulated evidence rather than single breakthrough observations. Additional parallax measurements, improved stellar population models, and better galactic dynamics simulations will gradually constrain the possibilities. The resolution might take years, but the eventual consensus will be built on much more solid foundations than current preliminary findings. The composition legacy extends far beyond 3I Atlas itself to the broader science of interstellar object characterization. The JWST, SphereX, and Hubble datasets establish templates for studying future visitors. Analysis techniques developed for 3I Atlas will be applied to subsequent interstellar comets with improved efficiency and sophistication. This cumulative improvement in technique and capability represents one of the most important outcomes of 3I Atlas science. Each interstellar visitor teaches us not just about its own properties, but about how to study the next one more effectively. The survey-era transformation promises to change interstellar object science from individual case studies to population statistics. The Rubin Observatory's expected discovery rate of multiple interstellar visitors per year will enable comparative studies that are impossible with current small sample sizes. Population science reveals different insights than individual object studies. Statistical distributions of composition, size, activity level, and orbital characteristics will constrain models of planetary formation processes across different stellar environments. Rare objects will be identified as outliers rather than mysterious anomalies. The career-defining aspect for current graduate students and postdocs deserves recognition. 3I Atlas represents a generational experience that will influence research directions and collaborative relationships for decades to come. Scientists who cut their teeth on interstellar visitor observations will carry that expertise into future leadership positions throughout the astronomical community. These researchers will design the next generation of survey instruments, develop improved analysis techniques, and train subsequent generations of scientists. The intellectual infrastructure built around 3I Atlas will compound over time as knowledge and expertise accumulate. The myth versus memory preservation challenge highlights the importance of maintaining accurate historical records alongside cultural interpretations. Future historians studying early 21st century astronomy will need to distinguish between what scientists actually discovered about 3I Atlas and what popular culture imagined about it. This documentary and similar efforts to clearly separate peer-reviewed findings from speculative interpretations serve as historical documents for future scholars. They preserve not just the scientific results, but the process by which those results were obtained and the cultural context in which they were interpreted. The international collaboration templates established for 3I Atlas create precedents for future multi-facility campaigns. Data sharing agreements, observing time allocation procedures, and coordination protocols tested on this object provide proven frameworks for responding to future discoveries. These institutional innovations may prove more valuable than the specific scientific results from 3I Atlas. Effective collaboration mechanisms enable better science on all targets, not just interstellar visitors. The visual legacy encompasses both scientific imagery and artistic interpretation. The first Atlas detection images, Hubble's teardrop-shaped coma photographs, and JWST's molecular emission spectra will become iconic representations of early interstellar visitor science. These images will appear in textbooks, museum displays, and popular science presentations for decades to come. They document not just 3I Atlas itself, but the state of astronomical technology and technique in the mid-2020s. The closing montage of discovery moments tells a story of human capability expanding to meet cosmic opportunity. From ground-based detection through space telescope characterization to spacecraft coordination, the 3I Atlas campaign demonstrates international cooperation at its finest. The Starfield fade connects this specific visitor to the broader galactic context in which such encounters occur. 3I Atlas represents just one example of the material exchange that occurs constantly between stellar systems throughout the galaxy. Its visit reminds us that planetary formation is a galaxy-wide process, not a local phenomenon unique to our solar system. The post-credits guidance for tracking future developments serves practical purposes for interested viewers. NASA's 3i Atlas webpage will continue updating orbital predictions and scientific results for months or years to come. ESA maintains similar resources for space telescope observations and mission updates. Reputable science news outlets provide summaries of peer-reviewed results as they appear in astronomical journals. These sources distinguish between preliminary findings and established conclusions, helping general audiences follow the gradual development of scientific consensus. The institutional framework for studying interstellar visitors continues evolving based on lessons learned from 3i Atlas. Survey capabilities improve, alert systems become more efficient, coordination mechanisms become more sophisticated. Each visitor teaches us how to study the next one better. Perhaps most importantly, 3i Atlas normalizes the concept of our solar system as part of a larger galactic community. Material moves between star systems. Chemical signatures from other stellar environments occasionally visit our instruments. We live in a dynamic galaxy where planetary formation processes can be studied through samples delivered directly to our scientific facilities. This perspective shift, from cosmic isolation to galactic citizenship, represents the deepest cultural impact of interstellar visitor science. We're learning to think of ourselves not as residents of a unique and isolated planetary system, but as participants in galaxy-wide processes of stellar and planetary evolution. The traveler from another star has delivered its message, shared its chemical secrets, and demonstrated the interconnectedness of planetary formation across vast scales of space and time. The conversation will continue long after 3i Atlas has returned to interstellar darkness, carried forward by the data it leaves behind and the expanded perspective it brings to our understanding of our cosmic neighborhood. We met a messenger from deep time and distant space. We learned what it had to teach, and we prepared ourselves to learn even more from the next visitors who will surely follow in its wake, carrying their own ancient secrets across the vast darkness between the stars.